Chapter 4, The Light Fantastic. Trembling with tenderness, lips that would kiss, from prayers to broken stone. And that was by T.S. Eliot from The Hollow Men. As the 20th century got underway, sobering discoveries in relativity and atomic physics electrified the New Age. These were wonderful discoveries that excited imaginations and reordered our appraisal of our place in the universe. Here was the discovery of the atomic nature of living matter, consisting of parts, atoms, that determine everything that you and I are, and discoveries of the diminutive reality of that matter. Here were the discoveries that showed the insignificance of mankind and the earth as but a mote in the vastness of space. These were discoveries that displaced and diminished man's self-image. These discoveries followed hard on the heels of the Wallace-Darwin theory of evolution, and they left man already suffering from the remoteness of God, with no meaningful place for God in the emptiness of space, no place for him to be, no role for him to play. All these discoveries left little absolute permanence in the picture of reality. There existed only the elements themselves, vast empty space and time. Even these had no permanence. Matter itself, not just its shape and form, could be entirely converted into nothing but the energy of motion. Space and time were made elastic, dependent on one's particular point of view. Certainties became relative. Man became animal, soul became id, but for all that had been lost, much had been gained. Gone were myths, with their passing, new freedom gained, and some small found part of the permanent truth. Michelson and Morley's observing changes in the speed of light and Einstein's postulating that the speed of light is a constant were signal events in understanding the nature of space, time, and matter. But the study of light was to reveal even more startling facts about its nature and the nature of reality itself. This next section is entitled Quanta. At the turn of the 20th century, the study of light raised other problems besides the issue of an ether. A number of physicists had been trying to figure out how light is radiated from hot objects. The way light and heat are radiated from an object, of course, depends to a great extent on the condition of the object's surface. But every object that is left alone to come to a constant equilibrium temperature reaches a point where it radiates as much energy in the form of heat and, if it is very hot, light, as it absorbs from its environment. A white object reflects most of the light that falls on it and usually radiates only a part of the heat that reaches its surface from its interior. But a black object has rather ideal properties. A perfectly black object absorbs all the light that falls on it and radiates all the heat that comes up to its surface. This makes it a perfect radiator. A black object heated in a very hot furnace radiates heat in a fashion that depends on nothing but the temperature to which it has been heated. More than this, anyone who has ever been around furnaces knows that as the temperature goes up, the color of glowing hot black coals goes from dull red to a cherry red to orange, yellow, and white, and then as it gets still hotter, the furnace interior takes on a bluish hue. The question that physicists wanted to answer was, what is it in the nature of this process of radiation of heat and light that determines just how much infrared heat and how much red, yellow, and blue light is radiated by a perfectly black body when it is glowing white hot. Now, if this seems like a perfectly esoteric and academic problem, that is just what the physicists thought as well. It was a perfect problem to demonstrate their mathematical acumen. The problem should be straightforward. Indeed, there seem to be many different ways to work out the details of this black body radiation problem. There was just one difficulty. Every time the problem was worked out, the result proved to be preposterous. The attempts predicted that more and more radiation would be emitted at shorter, bluer, and shorter wavelengths of light. The theory said that the total power, kilowatts of radiated energy, would be infinite. Such results are clearly wrong, but all efforts that conformed to the classical laws of physics kept yielding this same result. In 1900, Max Planck finally supplied the correct answer. After more than a dozen tries that led to the same incorrect answers everyone else had obtained, he figured out a way to finesse the correct answer. To do so, he had to make an assumption that even he did not believe. But it worked. He assumed that light is radiated not continuously, as had long been assumed, but in jumps and spurts that release packets of energy called quanta. In a way, this hypothesis was not so strange. It was already known that when gaseous material is heated, it emits radiation at specific wavelengths. Of course, each atom emits its little contribution of energy at some specific energy-dependent frequency. What if this always happens? What if each atom emits a discrete amount of radiation so that it rapidly cools as it releases its excess energy until it again absorbs more energy? Planck assumed that the radiation emitted by the walls and objects in the box had a discrete amount of energy that was proportional to the frequency of the radiation. This simple hypothesis of light as quanta turned out to describe perfectly the radiation streaming from a white-hot black body. Despite appearances, Planck's theory of light was not a reinvention of Newton's corpuscular theory. It had been assumed that light waves were produced when electric charges were moved back and forth, much as waves are produced when a stick is moved back and forth in water. In Planck's new description, the radiation of light was more like the effect of tossing a stone in the water. The energy went out in one lump. Planck thought these quanta would radiate out and behave just as Maxwell's theory of electromagnetic radiation predicted. It was simply necessary to assume that when the energy of light or heat is emitted, it comes out in little chunks of energy. 5 years later, Einstein brought this description of the quantum nature of light full circle. He showed that experiments carried out by Leonard at Heidelberg proved that light is also absorbed in chunks of energy. In these experiments on the photoelectric effect, ultraviolet light of different frequencies was found to be knocking electrons out of metal surfaces. What was of interest was the fact that the electrons did not behave as though they took time to build up enough energy from the light wave to break free, but rather would pop off the metal surface as soon as exposed to the light. Moreover, the energy of the electrons coming off the surface did not depend at all on how strong a light was shining on the metal surface. It depended only on the frequency of the light. The bluer, higher frequency light kicked the electrons out harder. The lower the frequency of the light, the less energy the electrons had when kicked off the surface of the metal. This showed that the energy of these electrons depends on the light's frequency, just as Planck had assumed in his solution to the black body radiation problem. Thus, both when emitted and when absorbed, light behaves as though it consists of quanta, chunks of energy called photons. And yet light must still obey Maxwell's equations. Light is still a wave. It may be radiated as a chunk, and it may still be a discrete chunk when it is absorbed, but it is also a wave. Light acts both like particles and like waves. This prickly pear would cause no end of mischief. How can electromagnetic energy spread out like a wave to the ends of the universe and yet still be deposited all in one neat package when the light is absorbed? Strangely, in 1905, Einstein had elevated Maxwell's equations to the height of an absolute principle in his theory of relativity, and yet cut away that principle's underpinnings with his theory of the photoelectric effect. Together, Planck and Einstein had created the greatest paradox ever to exist in science. If you aren't a physicist familiar with the intricacies of the wave-particle duality problem, the fact that one experiment gave wave-like results and another gave particle-like results for light may not even seem odd, but let us look a bit closer to see what kind of fantastic quandary this wave-particle duality of light leads us into. Consider the double-slit interference experiment that Thomas Young performed. In that famous experiment, light from one source illuminates a screen with two narrow and closely spaced slits to let a small bit of light through a second screen. These two slits now serve as two light sources that, because they are so close, permit the waves of light from one to interfere with the waves from the other. As the light passing through the two slits falls on the screen, the place where the crest of the wave coming from the right slit meets the wave crest from the left slit produces a bright band of light. Where trough meets crest, however, the two cancel out and the screen is dark. Thus, the presence of the second slit produces a pattern of bright and dark bands on the screen. This interference pattern of light and dark bands on the screen serves as a signature for the presence of a wave and proves the wave nature of the light. But what happens when we do this experiment with single particles of light? What happens when the light intensity is so low that only one photon at a time goes through the apparatus? Now we have a situation in which a single photon must go through either the right or left slit in the apparatus. With such a dim light source, we cannot see the interference pattern directly, but must use a photographic plate to find out where the photons are going. After enough photons have gone through the slits to build up an image on the plate, we discover the same interference pattern as before. If we close either slit in the screen and repeat the process, however, we see no such interference pattern. We are forced to conclude that every single individual particle of light that goes through one slit in the screen interferes with itself as it goes through the other slit on its way to the photographic plate. This single photon, this single piece of light, is at once a particle that causes a single grain in the photographic film to darken at one single point, and a wave that passes through both holes in the screen and fills all space in all directions at the speed of light. Think of one photon being emitted. It is a brief train of electromagnetic waves that speed away at a speed that Einstein's relativity has shown is the fastest anything can go. The wave passes by object after object, perhaps going into space, perhaps passing planets and stars as its spherical waves move out, passing by things without disturbing them, as though the wave had not passed that way at all. Suddenly it encounters some single atom somewhere, and all the energy of the entire wave is instantly deposited in this one spot. The only way we can imagine that the entire energy can be instantly gathered into one place is if it was always in one packet of energy in the first place. That leads to several problems, however. First, waves spread. No matter how tight the packet of waves, they would rapidly spread enough to allow us to split off some of the energy. But this doesn't happen. The photons act like discrete pieces of energy. Second, what would that idea do to the wave behavior of light? How could we explain the interference of light in the double slit experiment? What complicates this picture even more is that if, in the double slit experiment, we attempt to find which hole the photon actually passes through, we either fail or we destroy the interference pattern of the double slit experiment. Efforts to pin down whether we have a particle or a wave end in defeat. In certain types of experiments, wave phenomena experiments like the double slit experiment, the photon seems to be everywhere at once, whereas in other experiments, the photon is a particle to be found in one tiny spot only. But things are even stranger. In 1967, two physicists at the University of Rochester in New York, R.L. Flager and L. Mandel, carry out a variation on Thomas Young's experiment in which two light sources, lasers, one for each slit, were used as the source of the photons rather than a single light source shining through two slits. They found that a single photon created in and coming from one laser actually interferes with itself as it is created in and comes out of the other laser. What makes all this so much more confusing is what happens in such experiments when they are carried out using ordinary pieces of matter instead of light. Light is a form of energy, but as Einstein has shown us, energy and matter are just different forms of the same thing. If light waves of energy behave like particles, is it possible that ordinary particles of matter behave like waves of energy? Does it make any sense to speak of, say, a football wave? What is it that was going on so many years ago? What do those happenings tell me now about the nature of reality? The answer must lie in these memories somewhere. But what happened then? Somehow, pondering everything I have learned about atoms and wave particle duality has jogged other memories of long ago. What has become of all the moments we spend together? What has become of that love I dimly know was once the thing that filled every day? What did we do and say? These are the questions that decades later leave me searching so many blank pages of my old memories. They are the questions that echo about at times half noticed until a word cues a memory of something important, something that makes me say, how could I have forgotten? How could I have forgotten the diary? I kept a diary that year, only that year. Every day I made an entry and then returned the diary to the back of the top right-hand drawer of my dresser. I left that dresser years ago when I moved away to college, returning only for visits. I moved many times over the years, as did my parents, but eventually, with their deaths, all their things were parceled out, and that dresser came back to me. I set it aside for storage space. But what had I done with the diary? Where was it? Probably in some box among hundreds of others in the basement, where water had damaged some beyond recovery, or might it still be in that dresser drawer? Coming back into my storage, I searched out that drawer, and there was the diary, after almost 5 decades, still sitting in the same spot at the top of the right hand drawer, just as though I had put it there the day before. I opened it. Tuesday, January 1, 1952. There it was, my life. There she was once again, living in my mind once again. Wound up an evening of a show, TV show, my favorite Spy, and a stay at Marilyn Zender's house at 1:40 a.m. I awoke at 10:45 and made a date for a tennis game at 2 doubles. MAZ wore shorts, red shorts. The temperature reached 80 degrees that day. After tennis, we went to her house. It was a lovely day. Seal came to our house and took a picture of me holding Maz in the air by her ankles. I left about 5. Tommy Whitson, best friend, cohort in crime, called and we went to the show Distant Drums and lead out fraternity promenade dance. While I was out, a girl called for me. Red shorts. That was meaningful. That was the time of short shorts. I had forgotten about that picture. I did not get a copy of it, so it is now just dimly refreshed memory of the three of us in Marilyn's front yard. I was barely able to clear her 106 pounds from the ground. Somewhere in that faceless memory, I catch images of the pines and of laughing. Wednesday, January 2nd. Telephoned Marilyn. At about 1 o'clock, my mother and I went to Elvina Lohman's house for lunch. I am sure that was not what I would have freely chosen to do. In Elvina's house, one touched antiquity. 1890 was palpable. Elvina was slim, tall, pleasant, and old. Elvina's world was something made out of darkness, somber colors, oppressive decor, with black crinkled lacquered empire pieces that then were still too recent to be anything but old furniture. I went to town, bought a record, don't know the name of it, for 50 cents, Anima. I didn't like the opera, but the price was right. I called Maitland twice. At about 7, no answer. She called me at about 8 and asked me to come over. I did. Maitland had been my girlfriend for about a year. We were entirely unsuited for each other in every conceivable way, and I think in some ways we thought we were equally unsuited for anyone else. That kept us together, longer than we should have been. She was a year ahead of me in school. Her father was rather well-to-do. She belonged to the right sorority and drove, with total abandon, her father's brand-new ivory-covered Chrysler convertible with tan leather seats. She claimed she would have preferred 3 Dodges for the same money. I can hear her to this day. 3 times as many to wreck. She was from the social set in which, when she turned 16, her mother's friends would ask when she would start smoking. I did not like her smoking. I liked even less its use as a social litmus of priggery. But we had our clandestine affair, such as it was. We would go to the Mountain Brook Country Club for lunch on Saturdays and play tennis. She was athletic. She was coached by the club pro. In tennis, she beat me. She always beat me. And then we would go out onto the golf course, cross into the woods, and lay between the club and her house, and there in the grass spent our time together. At other times, she would fill the convertible with girlfriends and me, and we would fly around the hills of southern suburban Birmingham as though we were trying to kill her father's Chrysler in its first year of life. But before long, mother wanted daughter to see more of other boys and less of me. We still saw each other. She would phone me to come over at night, and I would walk the back way streets to reach her house. One time I had come over while her parents were out. They pulled in without us being aware they were there. The first we knew, we heard the key in the front door. I bounded for the stairs to the basement garage. Maitland quickly hid the flush in her face and whatever else. I hit the top of the steps just as her father rounded the entrance to the den, only 5 feet away. I was trapped there. I could not go down the steps. The steps would have made too much noise. They had come into the house so fast that I had not even had a chance to close the door to the basement. I was standing there against it. He paused. His wife spoke to him, and this gave me a moment to act. Slowly, quickly, ever so silently, I pulled the door almost closed as her father, a ponderable man, entered the room. He entered. I had not quite shut the door. The latch would have made too much noise. I was not held in high regard by her mother. I was hated by her father. I shudder even now to think what her father would have done had he found me there. I held my breath. Breathing would have made too much noise. "Maitland," he yelled, "you leave this door open?" His heavy body twisted the floorboards into sounds of incrimination as he stepped 3 more steps toward me. He stopped. He put his hand on the door, paused as though Hitchcock were directing the scene, and then closed and snapped the latch. I stood there for an hour. The voices eventually quieted into distant rooms. I took those steps one by one, each step cut into 100 partial movements. I took those steps listening, sounding the house out with each muscle flexed, taking a full hour for the 18 steps. And finally, out the garage door, through their yard, I dashed, hoping no one would glance out a window, running through their backyard, their neighbor's backyard, everybody's backyard, and out into the next street and safety. It is, as I judge now, attributable to that fair Maitland that today I must take to Norman daily for my blood pressure and monitor the progress of my heart's arrhythmia. But all of that was before I met Marilyn. Before the turn of the 20th century, when even the reality of atoms was still being contested, the raisins on a marshmallow picture of atomic structure was replaced by the Rutherford picture of the atom. This is the concept of the atom as some Lilliputian solar system with a positively charged sun-like nucleus surrounded by a swarm of infinitesimal planetary electrons scurrying about in the empty space around the nucleus. But how do these electrons keep from falling into the center of the atom? The electrons should be moving rapidly around that nucleus on orbits, the way the planets move around the sun. If they did that, this moving around and around should stir up light waves in the ether. But that would cause the electrons to lose energy and fall into their sun. If this were the way the world worked, everything would disappear in an instantaneous flash. The discovery that light is emitted only in packets of energy, however, made it possible to explain in part how atoms could radiate only under special conditions. Atoms, it seems, radiate only when there are packets of energy available, enough to create a whole photon. With this idea, Niels Bohr found a way to explain the structure of simple atoms. He proposed rules that determine special stable orbits for the electrons to circle in without radiating away their energy. The scheme Bohr invented worked after a fashion, but Bohr could not explain why these special rules should work. An adequate answer had to await the development of quantum mechanics. That development greatly depended on the insight of the French prince Louis de Broglie, who was studying for his doctorate at the Sorbonne. He had begun by studying medieval history, but had changed to physics when told of the wonders of relativity theory by his older brother Maurice, then in the vanguard of new investigations in physics. Basing his ideas on Einstein's equivalence of mass and energy and the interpretation of light as both wave-like and particle-like, de Broglie proposed that everything must have both a wave and a particulate nature. I had a sudden inspiration, he said. Einstein's wave-particle dualism was an absolutely general phenomenon extending to all physical nature, and that being the case, the motion of all particles, photons, electrons, protons, or any other must be associated with the propagation of a wave. De Broglie presented his thesis to Paul Langevin, at the time France's leading physicist, and also at the time having an affair with one Marie Curie. Despite such distractions, Langevin found time to send a copy of de Broglie's thesis to Einstein for the humor of it, but Einstein quickly realized the great significance of de Broglie's theory. He wrote back to Langevin that de Broglie had lifted a corner of the great veil, and so he had. Some years later, Einstein had the opportunity to lift another veil, alas, that of the same Marie Curie, as he and Marie vacationed together in the Swiss Alps. But then, that is another story. In his monumentous thesis, de Broglie showed not only that light is a wave that acts like particles of matter, but also that electrons, protons, and indeed all types of matter act like waves of energy. The reason why electrons inhabit these special Bohr orbits in atoms is that the electron waves can resonate in these orbits just as sound in an organ pipe can resonate at certain frequencies and not others. The de Broglie wave of the electron fits exactly an integral number of wavelengths into the electron orbit. But de Broglie's very success turns out to confirm facts that simply do not make sense. What does it mean for a particle to behave like a wave? How can a quantum of light, a photon, also behave just like the electromagnetic waves that Maxwell had described? As more and more experiments have ferreted out this wave-particle behavior of photons, electrons, and even the atoms that we are made of, it has become clear that reality is nothing like what it at first had seemed to be. Stitch by stitch, the whole fabric of reality, so carefully woven together by classical physicists, was unraveled into a plethora of confusing facts. Matter was not matter, but waves and energy, the stuff of no more than motion. Waves of light were as much particulate as waves of energy, and neither space nor time had any more than a relative meaning. There ceased to be any cohesive picture of reality. Physics had run out of pictures to explain its tapestry of colors. One by one, the discovery of physics undermined every vestige of the classical picture of an objective physical reality made of immutable matter existing in the infinite box of space and running to the tempo of a divine clock. In Einstein's hands, matter had become mutable to the energy of its own motion. Matter had become somehow a wave, a whole world but ripples on a great pond, an undulation of itself in a non-existent ether. Light had oscillated from Huygens' waves to Newton's corpuscles, back to Young and Maxwell's waves, and then to the packets of Planck and Einstein. Paradoxically, it had then finally become both at the hands of the little French prince. The picture was dizzying, stupefying, a Picasso collage pasted together from a collection of shattered ideas. Much would have to be done before waves and particles, matter and energy, could all be put back together again in one coherent equation. But as quickly as this old quantum theory had come, it too passed, inadequate to explain any but the simplest atoms. Bohr's picture of the atom's structure, only a model of what might have been reality, became merely a step along the way, a transition to quantum mechanics. Thursday, January 3rd, 1952, awoke to a cloudy day, called Marilyn. She had a party for 2 p.m. to 4 p.m., probably for her sorority sisters. I went to town, bought this diary, and again looked at records but found nothing. Came home and called the Emiru, Maz, and set a date to come over at 7. I walked over. We talked and read poetry and did other things. Yes, the word trouble is inserted here in small letters together with some sort of scale indicating 2, the number 2, quote unquote. I don't know what the scale meant, but I believe the top of the scale would have been about 4. Watched television spasmodically, left my book of poems there. Friday, January 4th, a gray day again today. I called Marilyn. We decided to play tennis. I put out the Christmas tree, my chore, and left for the tennis courts. I beat her 6-2, and then we went to her house. I picked up my book of poems and a poem she had written, which said, in effect, that she thinks she loves me. Saturday, January 5th, went to Maitland's. She was packing to leave for Stevens. She cried because she did not want to leave. I felt sorry. She was listening to the Hangout. Strange how music can put you in such a mood. I left about 2:25, called Marilyn from Hills in Mountain Brook to tell her I would be there in 30 minutes. We played doubles and won. Then at her house we played chess. I walked home and called Maitland to say goodbye. She called back at 7. I went to Homewood to the movie called The Golden Horde. I won't see Maitland again till June. I feel sorry, but I love Marilyn. What a store of memories and of emotions. I had forgotten so much. I had forgotten I used to call Marilyn my Amuru. It's Babylonian, Akkadian word that means donkey. I used to make her mad. It used to make her mad, so I teased her with it. Funny, all these memories. Strange how deeply they reside and how one memory pulls out the next like links in a chain until at times you find that even the subtlest thoughts you had decades ago are still hidden somewhere inside you. Even the way the words were written on the page is tied to thoughts that went through my mind as I wrote down